Good afternoon. I thought I'd just try to make one more today. Central limit theorem is probably one of the more complex ideas. So I really thought I'd see if I could explain it my best. Now, there's tons of stuff online. Know that I've always said like if you want organic chemistry tutor does an amazing job with this stuff. If you don't like the way that I explain it, the videos from this book and stuff, they're okay, but he also goes into calculus a little bit, so maybe don't use his for this, but just to understand the concepts. I'm gonna do my best to explain what the central limit theorem is. It's kind of an interesting concept, um, and I will try my best to show you like exactly how to do it. So here's 6-4. I'm in the intro to stats. We're talking about the central limit theorem. So that I spelled wrong, which is great for me, right? There we go. So what is it? What's the central limit theorem? Okay, so basically it's just a way that we can estimate things. Sometimes we don't have like enough of a population. So basically, sometimes we don't have a lot. So let's say we have a small amount of people. And this is like n is 10, n is 50, n is 1,000. Like no matter what we have, like the more people we have, like the closer we should be able to get like a bell shape or a bell curve. It's kind of what it works. But sometimes our populations aren't perfect, right? Sometimes, as we said, we could have one that's uniform. Sometimes we can have things that are uniform distributions, which is okay. Um, we could have stuff that's like curvilinear, or like it's curvilinear the other way. Sometimes we have stuff that's like a logarithmic, like it really depends on like the way that our populations look, right? So we could have all these different ways to like look at the population. Like sometimes, it's like going to be skewed to the right or skewed to the left. And we still want to be able to like do percentages and probabilities with these things, right? So what the central limit does or says, it's basically as long as we take a bunch of means, as long as we take sample means from it, as long as we're taking means from this, we take enough of those means, we're going to be able to create a bell curve from any single one of these populations. Now, I know that sounds kind of crazy. And how can we do that? Because these pictures aren't the same, like none of these pictures match. But as long as we have, I believe it's more than 30 means, as long as we have over 30 means to work with, we can make one of these pictures happen. So we can take no matter what crazy shape of the population, or even if we don't know like how the population really looks, as long as we're taking a bunch of different means from that, we can create a bell curve. And once we create a bell curve, we can use what we did before with z-scores, find probabilities and percentages. So that's pretty much what the central limit theorem is in a nutshell. We are basically we have to get enough means to create the normal distribution. And if we create enough means to create the normal distribution, then we can use things like z-scores to find it. I think that is, I think that's like the main idea, right? That's the whole main idea for all of this. But this is where we are, right? This is where we are for the central limit theorem and things like that. But basically, for this idea, we need enough means from our sample to create the bell curve. That's all it's really saying. So let's look at the book and go from there. So let's see. I'm in the textbook 6-4. Let's try our best with this. And then we said apply the central limit theorem. When the samples are large enough with at least 30 people, because we can get a mean for all of them. So we need at least n is 30. So it's not great. So it's not n equal to, and it's not the mean. So we just have to have more than 30 people we can use this. For all samples of the same size n, with n is greater than 30, the sampling distribution, so this is x bar, so can be approximated by the normal distribution of the mean with the standard deviation over the square root of n. So we just need n's bigger than 30 to use this. As long as our n is bigger than 30, guess what we can do? We can make one of these curves, and it doesn't matter how crazy the population looks. Okay, let's jump right into an example. This, we've got the tail on the right, it's right skewed, right? We got right skewed here. Remember, we have our mean. This is the population mean or our normal distribution mean. We have our standard deviation, which is going to be over the square root of n, okay? These are the two things we're going to need. So our original data is here. These are our commute times. Is this a normal distribution? No, it looks like this one, but we can make it into this. So let's get after it. Is a histogram of 1,000 samples means where each 1,000 samples includes 50 commute times randomly selected from the data. And if we take those 50 commute times, look, we're taking 50, that's more than 30. As long as we're taking 50 out of this crazy picture, it's like magic, right? We now have a normal bell curve where we can do what? Use z-scores to approximate this. Has a skew, but when we collect samples and compute their means, we tend to have a distribution that is normal. That's the whole idea. We can take anything. As long as we have more than 30, we take the means from each of them, we can make the bell curve. All right. Universal truth or truly remarkable that it works throughout the universe. Okay, that's fun. We can take a spaceship and we collect samples of rocks, weigh them. That sounds pretty fun. All right, so what do we have to know about this thing? The population has a mean of mu and a standard deviation. Simple random samples, all of the same size n are collected. So here, what do we take? We took 50, right? So this is the 1,000 commute times. And then we took what? We took 50 commute times. And that's how we made it. It's kind of wild. All right, so the mean of all values of x, the standard deviation of all values of x. So practical rules for real applications involving a sample mean. The population's having a normal mean. As long as it's bigger than 30, we can do this. So the mean will equal to this. The standard deviation, we just have to divide it by the square root of n. Then here's our z-score conversion. So the only real difference, so these are the three ideas that we have to deal with. We should be good. The standard deviation's got to be divided by the square root of n, and then our z-score conversion will be basically the same thing. But what are we doing here? We have to divide by the square root of n every time. That's the only addition. That's the only addition to these. That's the only addition to these. The original population is not normally distributed, and n is less than 30. cannot be approximated well by normal distribution. Do not apply. Okay, so if we're smaller than 30 and it's not in this shape. So if we originally started with this, it wouldn't matter how big it is. But if we're not with this shape and we're less than 30, we can't do this, which is fine. So you always check the requirements to make sure you can do this. Okay, what else we got? The individual value or the mean from a sample. Determine whether you're using the normal distribution with a single value for X or we have the mean value. Notice the difference. So if we're just taking these samples of values, you have to make sure we're dividing by the square root of n every time. Okay. So we have this little X bar, which means sample mean, so that's why it's right next to it as a subscript. Notice that this is noted as the standard error of the mean and sometimes denoted as SEM. All right, the big thing is, can we apply this thing, right? So here's our example. Let's make this happen. So American Airlines, Boeing uses 737 jets with 126 seats in the main cabin. In an attempt to create more room, an engineer is considering a reduction of seat width, great for everybody, from 16.6 inches to 16 inches. Adult males have hip widths that are normally distributed with a mean of 14.3 inches and a standard deviation of 0.9 inches. Find the probability that a randomly selected adult male has a hip width greater than this. Find the probability that 126 main cabin seats are all occupied with males with a mean hip greater. Like, what are the chances that it's one? What are the chances that it's all of them? And then for the aircraft seats, which part is more relevant? Results from part A, the results from part B, why? Is it more important that it's just one person's missing or everybody? So for the individual value, use methods presented, we are dealing with an individual value from a normally distributed population. We see the area that's shaded, which is fine. So let's start with just the one guy, right? So remember this from before. Our mean is 14.3. We have a standard deviation of 0.9, but we want to know if the year is 16.0. So we have to figure out what percentage is above this. We can use StatCrunch. We can use whatever we like. This little review from before. So why don't we use the StatCrunch one? So we can just go to StatCrunch. We can go to calculators and we can go to normal distribution. Okay. So this is our mean is what? Well, we have to turn this into a what? Into a z-score, right? To figure this out. But this is if it was already normally distributed. So we have 14.3, standard deviation of 16. And we want to know. Now, the first thing we have to do is find the z-score in order to do this. So the normal z-score is without this piece. So we have 16 minus 14.3. And then all we have to do is take this and divide by the standard deviation. That's the first step. Let's see what this percentage is. What's the probability that somebody's above this? So here we go. 16 minus 14.3, 1.7, and we're dividing this by 0.9. So we have 1.8888 is our z-score, or 1.89. So ready? 0, 1. We have 1.89. We want the other way, right? We want the other way. What chances this is 3%? That's 3% of people are over here. So this is like what we did last video, right? 3% are falling outside of it. And now we have the sample means of everybody, right? These are all the guys. So notice that is a lot higher, but the standard deviation is different. The standard deviation is now 0.1. So the standard deviation is 0.1, it would be different. So if we wanted to use the z-score with this formula, it would be what? It'd be still 16, it'd still be 16 minus 14.3. Our standard deviation is what? 0.1, and we're dividing this by the square root of how many people we have. And in this case, I believe for our n is would be 126 for this. So we got the first one, which is 3, which is great. We got the 1.89. Either way, we got that 3%, which is great. So the first part we did right. Now, because we were dealing with the mean of the sample and not an individual amount, we will use so for part B, we got to use the central limit theorem. So it's still going to be, our mean is still the same. And to get our standard deviation, so we need a difference in deviation. This is how they got the 0.1. So in order to use the central limit theorem, we have to use this first. We first have to get our standard deviation in order to do it. So all we have to do, it's nothing too crazy. So our standard deviation to get this 0.1 is going to be our what? It's going to be our regular standard deviation divided by the square root of n. That's what this is telling us to do. So divided by the square root of n, which is the square root of 126. I don't need two of these. 126, we want the square root of that. It's 11.22. So it's 0.9 over 11.22. And that's how 0.08, which they rounded to, 0.08, which they rounded to 0.1. This is what gives you the 0.1 here. And all I have to do is the square root of 126. So this is my new z-score. This is my new z-score. Which is nothing too crazy, right? It's nothing too crazy, our new z-score. So all we have to do is take the same thing, 16 minus 14.3. The mean doesn't change, right? You have 1.7. Now I just have to divide this by well, I need parentheses. So we know the top is 1.7. The bottom is 126. We need the square root of that. Oh, I just need a better calculator, that's all. So it's 0.1 divided by the parenthesis of 126, which is I want the square root of that. So the bottom is going to be that what? Which we already have from over here. It's the 11.22. So our final answer is just going to be 1.7 divided by 11.22, which is 0.66. There's our z-score. And why can we use this? Because we've got enough people. That's why we can cheat. That's why we can like make this happen. So all I'm going to do is change this to our new z-score is 0.66. And this would be, it says 25%. Let's see if I did that right. Oh, oops. They got 17. We got the 1.7 on top, but the bottom is just this value, which is 0.11. So I square rooted it twice. So we all make mistakes, right? We all make mistakes. Formula here is z. Your mean minus your sample mean, right? Oh, sorry, it's the mean you're looking for, or your X value that you're trying to find from the sample, minus the total mean over what? Whatever you get for your standard deviation, which we know was 0.1. I just had an extra one here. I already did the divided by the square root, so I don't have to do it twice. That was my only mistake. Guess what? We all make them, right? So the value is going to be that 16 minus 14.3 over what? R.1. So what do we get? 16 minus 14.3 divided by 0.1. That's how you got that 17. And if we go back here to this value, calculator, we want the normal distribution. We just want this the other way. And we just want this to be 17. It says it doesn't exist. Oh, yep, 0.00000001, or we can just round it to 0. So it is highly unlikely that all 126 males will have a hip width greater than 16. It almost doesn't even exist. If we do it this way, it should be like 100%. Oops. See, it should be like almost everybody falls within that range. So one person not being able to fit in these new seats would be 3%. Having an entire flight would basically be 0%. So let's see. Oh, we get to introduce hypothesis testing. All right, carefully examine the conclusions that are reached in the next example, illustrating the type of thinking that is the basis for important procedure of hypothesis testing, which we will go into next. If under a given extent, the probability of a particular result is very small, the observed variance significantly less than or same than what we expect. So based on this study, we'll see that yes, they can shrink those seats because the chances of all 126 people being there would not happen. So here we go. Here's our first real example. This is like our first actual example. Let's get after it. So let's make this happen. Remember, these are our three formulas. This is if you don't do it first, but basically it's X bar minus the mean over the standard deviation over the square root of n. This is going to give us our z-score. All right, here we go. Assume that the population of the human body temperatures has a mean. Here we go. Here's our first thing. Here's our mean, 98.6. Also assume that the population standard deviation, right? The population standard deviation is what? 0.62. Now our n is 106 people. And the mean body temperature for this, so this is for our sample mean is what? 98.2. If the mean temperature is really 98.6, find the probability of getting a sample mean of 98.2 or lower for a sample size of 106 people. Based on the result, is it significantly low? So all we have to do is try our best to figure this out. So in order to get this, we're just not going to make mistakes. We're going to take our time. We're going to make everything happen. So this is the same. This is divided by this, and then we have it. So let's start. So for our z-score, we want to do it in one step. It's basically going to be what? It's going to be what we get from our sample minus the total. So our sample is 98.2 minus 98.6 over 0.62 divided by the what? the square root of 106. That is how we get our z-score. So we're going to do the top, then we do the bottom, then we're going to put them together. So here's the first part. The first part is 98.2 minus 98.6. We should get a negative 0.4. The bottom is 0.62 divided by 106 square root. Notice that this is here. So our bottom is 10.296. And so here we go. So our answer is going to be 0.4, the negative of 0.4 divided by, oops. 10.216. So this is our z-score. Our z-score is negative 0.0391. Now notice, did we have over 30 people in our sample? Yes, so we can use this value. We just want to know, is this significantly low, right? So I'm just going to go here. It's between 0 and 1, and we just want to put in negative 0.0392. Or you could put 915. You can go as many as you want for your significant basis. To me, this is not significantly low, right? What are we at? We're at 48% of the population, 0.484 or 48.4%. This is not significantly low. This is about half of everybody. Okay, so I made a mistake somewhere. That's okay. Do we make mistakes? Sure. So we have the 98.6. And then we have the bottom, which we got was 0.62 divided by 106 square root of that. And you got the 10.29. How come I'm getting 10.29 when I'm putting it in? Well, this calculator isn't the best, so I'm going to use a different one. They got 0.06. We did not get it, so I'm going to use a different calculator. Just going to use Desmos. Did all the steps right. The calculator failed me. Isn't that exciting for me? So I'm going to take it right from here. All right, so equals parenthesis 98.2 minus 98.6 divided by parentheses 0.62 and then I want divided by the square root of 106. Sometimes these calculators, they aren't your best. If you didn't get the right answer, guess what? Things happen. So I got a negative 6.642. Let's just do the bottom, which was parentheses which was parentheses 0.62 divided by the square root of 106. Yeah, I got 0.06 again. Oh, see, when I put this in the calculator, they gave me 10.2. So we know it's really supposed to be what? 0.06 on the bottom, which will give us a what? A final answer of a negative 6.64. Now let's actually get that value in StatCrunch. Negative 6.64 It almost does not exist. It is definitely significant. It's almost never happened. So that's why it's significant. Isn't that nice? 6.64, 0.001. It's actually 0.00001. But either way, you can see that this is significant because this is much less than 0.05. We use technology, we get 0.000000155. That's exactly what I got. You can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's why it's the negative 11th power. That's the value. Cool. So this is significantly low. It's very rare. That's how it works. Correct the finite population. Oh, we've got something at the very bottom. So in applying the central limit theorem, our use of the standard deviation of the mean assumes that the population has infinitely many members. When we sample with replacement, the population is effectively infinite. When sampling without replacement, we may need to adjust the standard deviation of the mean. Here's the common rule. So if you are replacing stuff, the bottom should have this instead. So when sampling without replacement, the sample size n is greater than 5% of the population size. Adjust the standard deviation sample by multiplying it by its finite population correction factor. Cool. So if we use without replacement and we have a finite population, we have to adjust this. Remember what without replacement means? This means we have a fixed number. If we are replacing, it's an infinite number. So what does this mean? What does this mean when we're working with it? I really thought that'd give you a lot more information on this. So remember, whenever we have without replacement, n minus n over n minus 1. Well, what is this? Sorry. This big N is the total population. This is the N of your sample. This is the total population again. Then we subtract 1 for what's called degrees of freedom. And we'll get into that. But do they give us an example of this? They do not. Exciting. So when do we use this? So for our standard deviation of this, the standard deviation of the means, of the groups of means we're taking, normally it's this, right? Standard deviation over the square root of n. However, if for some reason they say without replacement, we use this instead. All right, we're ready for problems. I'm ready for problems. All right, 1 through 4, 5, and 10. Let's get after it. Here's number 1. All right, number 1. Medical researchers once concluded the experiments determine the Lisinpril drug that is effective in lowering systolic blood pressure of patients. Patients in the treatment group had their systolic blood pressure measured after being treated with this. Under what conditions can this sample be treated as a value from a population having a normal distribution? For number 1, I believe all it needs to do is needs sample greater than 30. I'm pretty sure that's all you need for this one to prove that it's right. And as long as you do that, you're going to be on point for this one. Yes, I just like to double check. All right, so what else? We did 1. Let's see what other ones we've got. 1 through 4. Okay, so I got to do all these in the beginning. 2. Sample weights of M&M candies are normally distributed. Ooh, 12 are randomly selected and weighed. Mean is calculated. Is it correct to conclude that the resulting sample mean cannot be considered to be a value from a normally distributed population? Is too small? Nope. Why not? Because it's already normally distributed. So we can. So it's double negative. We can consider it. Because it says right here that they're already normally distributed. So as long as it's already normally distributed, right? As long as we're already normally distributed, we're good to go. If it's weird and we have more than 30, we can change it. All right, let's go to 3. In general, what do these symbols mean? So this is the mean of the sample we have. And this is the standard deviation of the sample. What are the values of this for 36 selected with this? Okay, so we have to just do this piece. So what are the values of this? So the mean's the same for this one. 3 for number 3 is going to be the same. So it's not going to change. So it's still going to be 100. Now, the only one that's going to change is the standard deviation. So normally we do the standard deviation of the mean, but now we have to take the original standard deviation, which is what? We have to divide it by the square root of n. So all we have to do is take what was normally 15 and divide this by the square root of how many people do we have? 36. And why are we allowed to do this? It's more than 30. I'm going to keep using decimals as my calculator. And it's way easier to use. It's 2.5. Boom. We made it to 4. Annual incomes of statistics students are known to have a distribution that is skewed to the right. Okay, cool. These are skewed to the right. Assume that we collect a random sample of annual incomes of 50. Yes, we can. More than 30. Awesome. All right, that was 1 through 4. Nothing too crazy about it. Let's hopefully 5 and 10 and 15 will give us one to actually do, because I want to do one. Let's look at 5. Using assume that the amounts of weight of college students gained during their freshman year with a mean of 1.2 and a standard deviation of 4.9 to get the freshman 15 pounds. One male college student is randomly selected, and the probability has no weight gain during his freshman year. That is a probability during his freshman year. His weight gain is less than or equal to 0. Okay, so basically all we need to do is this z. I'm going to have it look like that. So I don't mess it up. So what is it? It's our x minus the mean over the standard deviation of square root of m. Nothing crazy about this. So his is going to be what? 0, right? So these two aren't going to change. So we say the normally distributed, the male college student during their freshman year is distributed with a mean of 1.2. Okay, so basically, I believe it's 1.2 minus 1.2 over the standard deviation, which is going to be 4.9. Which is 4.9 divided by the square root of Doesn't give us the n. That's okay, because 0 divided by anything is still going to be what? No matter what this value is, right? It's still going to be 0. So our z is 0. So let's see what it is. I'm assuming it's going to be 50%, but we might as well plug it in and double check that this 0 is in fact 50%. Yep, 0.5, 50%. We don't even get a picture. That's annoying. All right, it says 50%. So easy. We're right in the middle of the graph. We got 50%. Let's try B. 25 are randomly selected. This is less than 30. But it says it's normally distributed, so we can do it. Find the probability that is less than or equal to 0. I believe this is also going to be 50% for B. Well, I just looked it up and there was a mistake here. So let's figure it out. Let's see where my error was for 6-4, number 5. You know why? Because we all make mistakes. So I got to do 5 again. Assume that the amount of weight cost gained is normally distributed with a mean of 1.2 and a standard deviation of 4.9. Okay, so let's figure it out. Oh, okay, I see what it is. Guess what? I made a little mistake. So, ready? So this is the weight change. Okay, so that's why it's going to be 0 minus. I just didn't read the question well enough. You know why? We're all human. We all make mistakes. So our z squared assume that the amount of weight male college students gain during their freshman year are normally distributed with a mean of 1.2 and a standard deviation of 4.9. Now, it doesn't say, it just says, it doesn't say what we have, but we can use this one to find it. We don't use this because we don't have to use the means, it's just a normal one. So I believe this is what we have to do. So it's going to be a negative 1.2 divided by 4.9. Then we have to just look it up because that's our z-score. So we have, and I just have to move this business up. If it will let me move it. Here we go. So we have negative 1.2 divided by 4.9. So I got a negative 0.2448 as my z-score. And here we go. I got 0.40. I got 40%. Let's see if that's right. We got it. Well, they rounded to 41. I probably didn't put in enough decimal points, but 40%, 41, I'm pretty close. I'm feeling good. Feeling good about it. Let's try the next one. So B says there's 25 college students randomly selected. Find the probability that their mean weight gain during the freshman year is less than or equal to 0 kilograms. Why can it be used? It says it's already normally distributed. That's why we can use it. 25 male students are randomly selected. Find the probability that their mean weight gain during their freshman year is less than or equal to 0 kilograms. So if we have 25 of these guys, let's see. So it's still going to be 0 minus 1.2 over 4.9 divided by the square root of 25. I believe this is what we have to do for part B. So we have 0 minus 1.2. This is 4.9. This is the square root of 25. All right, so my z-score here is going to be negative 1.224. Oops. Negative 1.2244. I got 11%, and so did the book. I love it. Why were we allowed to do this for part C? It's because it said it was already normally distributed. Okay, let's see what else we got. Is there a, no, just A, B, and C. Cool. All right, what else we got? Let's look at 10, 15, and 18. Here's number 10. Involve applications to ergonomics as described in the chat. Okay, I'll do my best. According to the website torchmate.com, manhole covers must be a minimum of 22 inches in diameter, but can be as much as 60 inches in diameter. Assume that a manhole is constructed to have a circular opening with a diameter of 22 inches. Men's shoulder widths are normally distributed with a mean of 18.2 inches, a standard deviation of 1 inch. Based on the data, what percentage of men will fit into the manhole? All right, so let's figure it out. So let's do our best. So we need a z-score here. The first thing is we've got our x minus the mean over our standard deviation. That's the first thing. So we got guys at 18.2. We're going to subtract the mean, which is 22. We're dividing this by the standard deviation of 1.0. That's the first step. So here we go. It's going to be 18.2 minus 22. This whole thing divided by 1. Is it just divided by 1? Just 1.0? That's what it is. That's nice. So it's a negative 3.8 is our z-score. So I feel like everybody will be able to fit into this manhole with a z-score that low. I'm going with 100% or 0% because it's everybody less. We want everybody who can fit into that hole. We need the opposite of this. 99.999. So I'm going with 100% of people. I like it. It's to the right instead of to the left. We got 100% of folks. All right, so let's look at the next part. Assume that the Connecticut Evergreens Company employs 36 men. The suite is over 30. What is the probability that their mean shoulder width is less than 18.5? This result in money saved by making smaller manholes with a diameter. Oh, I love this question. Okay, so here we go. We want to see if we're gonna make this thing shorter. Or okay, so here we go. So we need this z of the means. See how it's a little bit different. So now we first need our regular mean, which is the same. So we got these guys whose mean shoulder width is less than 18.5. Sorry, normally it's 18.2 minus this 18.5. And what is our standard deviation is 1.0. But we have to divide this number by what? The square root of how many guys we got, which was 36. That's the main difference here. Okay, it's still going to be your x minus your mean of x. But this piece, this is the standard deviation of x bar, which means you need this piece here. Let's see what our new z-score is. 18.2 minus 18.5. This is just the number 1. This is the square root of what? 36. So now our new z-score, our z-score of the sample means, right, is negative 1.8. We gotta know, right, should we make the manhole smaller with this diameter? Why or why not? So we gotta really make sure that just about everybody can fit in this thing, right? So let's look at B. Now our thing is, I believe it was 1.8. Sorry, negative 1.8. We are at 90. Usually it's what? 0.05. I got 96% here, right? I got 96%. I'm gonna say do it. I'm gonna say save the money. We're only talking what? 5% of people not being able to fall into this thing. I like it. As long as it's more than 0.05, I'm going with it. So that's what my answer is. That's my reasoning. We ended up with 96% greater than 0.05. Let's shrink those manholes. All right, let's keep it going. And I'll do 50. I'll leave you with 18. Let's look at 15. Ooh, 15's got a ton. Cool. Yeah, I'll leave you with 18 to do. Here's 15. All right. Carries 200 passengers, has a door height of 72 inches. Heights of men are normally distributed with, so we have a regular mean, right? We got our mean of the population, which is 68.6. And a standard deviation of what? 2.8. The passenger selected, what is the probability he can fit through the doorway without bending? Okay. And the door height is what? Our x. Our door height is 72. So let's get the z-score for the first one. So what do I have to do? I gotta go x minus mean over SD. So here we go. It's going to be 72. Oh, sorry. Do I have it backwards? Height is 72 inches. I always have a moment. Sometimes I get confused. Yeah, it's x minus the mean over this. Perfect. So here we go. So x minus the mean over the standard deviation. So we've got 72 minus 68.6 divided by 2.8. I got 1.21, 1.214. And let's see how many guys fit through this door. 1.214. 88.8% of guys. So approximately 88.8% of guys fit through this door without bending over. Start bending down, right? Like leaning in. All right. Now, if half of the 200 passengers are men, find the probability that the mean height of the 100 men is less than 72 inches. Right. So let's do this. So it's the same idea, except it's still our door, right? Our mean is the same. The mean doesn't change, but it's just the mean of x. But here, our standard deviation, 2.8, has to be what? What is it we got? We got 100 men. So the square root of 100 is on the bottom. So just 10. We're just dividing, this is just equal to 10. It's just 10 on the bottom. So let's see what we get. 72. 68.6. 2.8. Square root of 100, or you can write just 10 if you want. It's up to you. All right, 12, what? 12.14? I guess this means we're all gonna fit. Isn't that wild? So if I put this in here, it's everybody. Okay, so I'm gonna look at what the book says for this one, and I'm gonna look at the question again. It says it's 100%. So let's see what B says. We're on 15. B says 100%. Wow. Okay, that's cool. I just didn't know if it was a trick question. Considering the comfort and safety of passengers, which is more relevant? Probability from part A, probability from part B. Why? Comfort and safety, I think just bending through, like it's not a big issue, so I wouldn't really care about it, which is more important. 88, 90% of all men, 88% of men will fit. Or if I take 100 guys, all 100 will fit. I don't know. Really think about that one. And D, why are women ignored in this case? Well, the women are ignored in this case is because the women will be on typically shorter, so we don't have to consider them. All right, that was the central limit theorem. I hope you learned something. I know going through these formulas again, I hadn't in a while, so I definitely remembered how they work. But yeah, just reach out to me if you've got questions. I thought this one was really useful, and take care.